difficult to reject the null hypothesis of no co-integration between the nominal exchange rate and relative price doubles. And very often the symmetry and proportionality conditions implied by PPP are also rejected. Okay? So then some researchers, they started looking at this power problem. So they thought, well, one reason why we cannot reject a unit root in the real exchange rate may be because the unit root tests have low power to reject the null hypothesis of a unit root, even though there is no unit root in the real exchange rate. Okay? So they investigate this problem of low power, and an important paper here is by Lothayan and Taylor, which we started looking at last time. So this paper looks at the real exchange rate using a long span of data, 2 centuries of data for 3 countries, and that's what we were looking at last time. Okay, so they collect data spanning 2 centuries in length for UK, US, and France. So they could make 2 real exchange rates, US versus UK and US versus France. Okay, so this is the log of the real exchange rate, deviation from PPP. And if PPP holds, then QT, the real exchange rate, would be a constant. But in fact, what much of the literature finds is that QT is far from a constant. It is extremely volatile, especially over the floating rate period after the breakdown of the Bretton Woods. So that's what they are looking at. So they construct this long data set, and then they apply the unit root tests. So this is for the dollar sterling exchange rate, first table. And they show that if you look at the full sample of their data, you can easily reject using augmented Dickey-Fuller and Phillips-Heron unit root tests. You can easily reject the null of no unit root in the real exchange rate. Second, they look at their sample up to the Second World War, 1945. Once again, you can easily reject the null of the unit root. Now, if you look at shorter time periods, like this is the post-Bretton Woods period of floating exchange rates, and this is the post-World War II period, okay, then you still cannot reject the null of a unit root in the real exchange rate. So what they are saying is, well, this seems to be happening because of the small power of the unit root tests over these short time periods of 40, 50 years or 15, 20 years. If you look at a long enough time period, you can easily reject the null of the unit root. If we look at the franc sterling, same, almost identical results. For the full span, you easily reject a unit root, suggesting that PPP holds in the long run. But if you look at the post-World War II or the floating rate period, you are unable to reject the null of the unit root. Okay. Now, once you find that you can reject the null of, so then they also do this for selected subperiods. Right? So instead of looking just at the post-World War II period of 45, 50 years, they say, let's look at some other 45, 50-year period. And if you take another 45, 50-year period, you also cannot reject the null of the unit rule. Only over here, even though this period is quite short, you're able to reject it, but in 3 out of 4 cases, you're not able to reject it. So they're saying it's the shorter time span which is the cause of the low power. Okay, so once they have established that the real exchange rate is stationary, you can reject the null of the unit root over the full sample. Then they want to see what kind of stationary process would describe the real exchange rate, okay, if it is really stationary. And so they try to fit an ARMA model to the real exchange rate. And basically, the ARMA model that they identify by looking at the autocorrelation structure of the data is an AR1 for both the real exchange rates. Only the first lag is significant for the sample partial autocorrelation function. So that indicates that an AR1 model is appropriate, okay, for both the real exchange rates. You can see the partial autocorrelation function cuts off after the first lag. Okay, so then they model both the real exchange rates as a simple first order autoregressive model. And so that's what they do over here. So they fit an AR1 model to the dollar sterling real exchange rate. This is up to the Bredensburg period of 73, and this is for the whole sample. Okay. So here you find the coefficient is 0.9, and this is the standard error. So it is close to 1, right? 0.9, but it is significantly smaller than 1, right? Even 2 standard deviations, they take you up to 0.96, but not up to 1. Okay? If you look at the full sample, we have something very similar, 0.89. So the other thing is that the coefficient is quite stable. Okay, they actually do a Chow test for the stability, and they find that there is no break, okay, in this time period. Then for the franc sterling, they find similar results. So for the full sample, about 0.78 and 0.76 up to the Bretton Woods period. Okay, so what do we conclude from this? Okay, so coefficients alter only very slightly when the floating rate period data are included, and there is no sign of a structural change during the floating period based on the Chow test. Okay? So the sterling real exchange rates against the franc and the dollar are adequately characterized as a stationary AR1 process. Higher degree of persistence in dollar sterling real exchange rates. The coefficient is close to 0.9, whereas for the franc dollar rate, it's 0.76 roughly. Okay, so the point estimates indicate that shocks to the real exchange rate are corrected at a rate of some 23% per year for franc sterling, because the coefficient is around 0.77, whereas only at 11% for dollar sterling, because the coefficient is 0.89. So half-life of real exchange rate shocks is about 6 years for dollar sterling and 3 years for franc sterling. So the half-life concept is the following. So the half-life is the period of time in which half of the shock is eliminated, because this is a stationary process. If there is a shock, then over time the impact of the shock will be eliminated. Half-life is the time in which 50% of the shock is eliminated. So for a stationary AR model, we compute the half-life as the solution to this equation. Okay, so in the case of the US-UK real exchange rate, we have rho equals 0.89. So then, taking logs on both sides, okay, so you can compute this. So the half-life for the US-UK real exchange rate would be log of 0.5 over log of 0.89. So if you compute this, what do you get? Can someone do this quickly right now? If you have a calculator. $5.94. Okay, so this is annual data, so approximately 6 years. And then for the other real exchange rate, it's the coefficient is 0.77, so log of half over log of 0.77. How much is that? 2.52. 2.52. Yeah. Okay. So about 2 years. Okay, so that tells us that for the US-UK case, the shocks are quite persistent, right? Half of the shock dies out after 6 years. So that means the adjustment or the reversion to the mean is very slow. But for UK, France, about 3 years, so the adjustment is faster. So half-life about 6 years for dollar sterling and less than 3 for franc sterling. And why is that? So that may be closer physical proximity of UK and France that might have caused, and the fact that they are close trading partners, UK and France, that could have caused better arbitrage, right? More integrated markets, so PPP works better. Half-life is shorter for UK, France compared to the US. Okay, now what else can you do with this to convince people that their model is a good model? They try to do an out-of-sample forecasting exercise. So they're saying, well, if our stationary AR1 model is really better than the random walk model, then it should give better out-of-sample forecasts of the real exchange rate. So they compare the out-of-sample forecasting performance of the stationary AR1 model against the random walk model. And so they do it in different ways. Okay, so these two models are the stationary autoregressive models, the AR1, and they're going to compare them with a random walk and a random walk with drift. And the way to do it is to compute the root mean squared error for each of these models and then look at the ratio. Okay? So you can see that at a horizon of 1 year, right, the ratios are quite close, right? 0.99, 95, 94. So, but 1 is still doing better than 3 and 4, which are the random walk models. And as you extend the horizon up to 5 years, then you can see that the improvement over the random walk becomes significant. The root mean squared error of the stationary model seems to be significantly better than that of a random walk with or without drift. And the same thing is true for the franc sterling as well. So So their stationary first order AR model produces better forecasts than random walk models. And this forecasting superiority increases with the time horizon, and that's what you would expect if real exchange rates are slowly mean reverting. Okay. So this slow adjustment coupled with the low power of conventional unit root tests accounts for the widespread failure of such tests to reject the null of a unit root in data for the float alone. Okay? So that's their conclusion, and they feel that in the long run, PPP remains useful as a first approximation. So that's a nice paper. Okay. So now this low power phenomenon can also be illustrated through a Monte Carlo exercise. Right? So the paper we just studied, they estimate this AR1 model, and for the sterling dollar, this is the regression that they got. Okay, so their coefficient is around 0.89. And with this coefficient, this is the empirical power function for the Dickey-Fuller test. So if the true value of rho is 0.89, then this is telling you, based on the length of your sample, what is the probability that you will reject the null of a unit root when the null hypothesis is false. Okay? So rho is smaller than 1 in all cases. So the unit root null hypothesis is false. You should be able to reject it. But you can see, if your sample size is only 15 years, the probability that you will reject the null hypothesis is only 6.3%. Okay? Even with 100 years of data, you will reject unit root with probability only 40%. Okay? So you need more than 200 years of data to almost certainly reject the null of the unit root when the true value of the coefficient is 0.89. If it is 0.95, then you need, even with 250 years of data, the probability that you can reject the null is less than 50%. Okay? So that just illustrates the low power of these unit root tests, like ADF test and the Phillips-Heron test. So, okay, so that's the low power. Now, what is also important here, so some people try to solve this problem. They say, well, okay, if we have only 15 years of annual data, then your power will be very low. Let's try to make it quarterly data instead. Okay, 15 years of quarterly data will give you 60 observations. Is that going to make your unit root tests more powerful? So you change the frequency of the data. Okay? The time span is harder to change, right? So instead, if you try to change the frequency, from annual, you go to quarterly or monthly, right? 15 years of monthly data, 15 times 12. So it's 180 observations. So that may give you more power. Is that correct? But it turns out that that doesn't work, okay? Because co-integration is fundamentally about what happens in the long run. And keeping the span of the data fixed, as you increase the frequency, you are not adding a lot of long-run information in your data, okay? You're probably adding a lot of noise, a lot of short-term noise. So that really does not help to improve the power significantly. You really need to increase the span of your data if you want to increase the power. So that's something very important in practice when you are doing a co-integration test or unit root test. Don't think that if you get daily data, you have many more observations, so your test will be more powerful. It doesn't work like that. Okay, so the Monte Carlo evidence of Schiller and Perron shows that we cannot circumvent this low power problem by increasing the frequency of observations from annual to quarterly or monthly, and thereby increasing the number of data points. Okay, because we are looking at the low frequency components, the long-term information, we really need a long span of data to improve the power of the test. Okay? So there are really two alternatives to increase the power of the test. One is you increase the span, okay? Use very long data sets. Another is you keep the span the same, but you add, make a panel. Okay, so instead of looking at one country with 20 years of data, you look at 50 countries with 20 years of data. So you make a panel data set. That is another way of overcoming the low power problem. Okay? So we've already seen one long span study, the Lothayan and Taylor, and you can just read through this few others. Okay, so long span studies like the one that we just saw they are generally more favorable to PPP. They tend to reject the null of a unit root, but they are also subject to some criticism. And one is that over very long data spans, you're combining data from many different exchange rate regimes, right? Gold standard, silver standard, Bretton Woods, post-Bretton Woods, and so on, okay? And during this time, real shocks over long periods may have generated structural breaks or shifts. So that is one general criticism. So if you're doing a long data span study, then it's important to also test for structural breaks. Then the other literature, the other way to improve power is to increase the number of exchange rates under consideration. Okay? So using a panel approach. So the time span cannot be increased, keep the time span the same, but add a number of exchange rates. Analyze them together using a panel approach. So just like we have unit root and co-integration for a single real exchange rate, it is possible there are panel unit root tests and panel co-integration tests. I'm not going to cover those in class, but if you are interested, you can learn in eViews how to do those tests. Okay? It's not really difficult. So I leave that to you. So when we look at panel-based tests, in general, we find more evidence in favor of PPP. It's just like the long span. But one thing we have to be careful about when we are looking at panel data, now in a panel data, the null hypothesis, suppose we have 50 countries in one panel. The null hypothesis is going to be that all 50 real exchange rates have a unit root. Okay? So if you are rejecting the null hypothesis, okay, then what does that mean? Does it mean that all 50 real exchange rates are stationary? Not necessarily. Even if 1 out of 50 is stationary, the other 49 are non-stationary, you're still going to reject the null hypothesis. Okay? So that's a problem. So the conclusion suggested by the panel studies may be misleading because of an incorrect interpretation of the null hypothesis. Okay? Null hypothesis in many of the studies is joint non-stationarity of the real exchange rates considered. Therefore, rejection of the null hypothesis may occur even if only one of the series considered is stationary. Okay? So therefore, if rejection occurs for a group of real exchange rates, it does not really tell us a lot. Okay? And we cannot conclude, therefore, that PPP holds for all 50 real exchange rates when you reject the null of the unit. Okay, so by and large, when we look at long span studies or panel studies, then we tend to find more evidence in favor of PPP. Okay? But even though we tend to find more evidence in favor of PPP, still the results are not really satisfactory. Okay? They're not really satisfactory, and that's why a very renowned economist, Ken Rogoff, has characterized the results as forming a puzzle, a PPP puzzle. So what is the puzzle? Okay. Okay, so first, for the long span, we have some doubts because it is combining real exchange rates across different historical periods and different nominal exchange rate regimes. So that's a question mark whether PPP really holds. And for panel data studies, as we just mentioned, most of the null hypothesis is that all the exchange rates have a unit root. So when you reject them, then that doesn't mean that all of them are stationary. Now, even if we assume that these problems are not significant and PPP holds in the long run, we still have a second PPP puzzle. Okay? Studies that do report significant mean reversion, so like the Lopine and Taylor paper that we just studied, we see that the half-life is quite large. Okay? So what this means is that shocks to PPP are very persistent. They seem to be dying out very slowly. After 6 years, only half of the shock is eliminated. So even if PPP does hold in the over a 200-year period, it seems to be extremely slow. The mean reversion seems to be extremely slow. Okay, so in general, the consensus is that the half-life of deviations is about 3 to 5 years. Okay, and that seems to be too long. Too long. Okay. So how can we explain this slow reversion of exchange rates? Could it be that real shocks? Well, for real shocks, like shocks to technology, shocks to taste, we think they should not matter much in the short run because they change slowly. Tastes are not going to change overnight. Okay? So real shocks may find it difficult to account for this theoretically. We will look at the evidence later. Second, if you look at nominal shocks, well, nominal shocks should not have any real effects over a 5 or 6 year time period. Nominal shocks have an effect when nominal variables are sticky. When nominal wages are sticky or nominal prices are sticky. And what is the time period over which prices can remain fixed? Okay? So in the standard macro literature, right, prices may be fixed in the short run because you sign contracts, and once the contract is signed, the variable cannot change over the life of the contract. But surely you're not signing contracts for 5 or 6 years. You may sign a contract for 1 year, 2 years. So any effects from nominal shocks should not cause the real exchange rate to be so persistent. Okay? So then the puzzle is, how can one reconcile the enormous short-term volatility of real exchange rates with the extremely slow rate at which shocks appear to damp out? So that's the second puzzle. Okay, so after Rogoff formulated this puzzle in the mid-90s, researchers tried to address this in 2 ways. One is allowing for underlying shifts in the real exchange rate. And there's a class of model called the Harrod-Balassa-Samuelson model, which we're going to look at. These models argue for the importance of real shocks in explaining deviations from PPP. We're going to look at those. And The other way is through non-linear dynamics, okay, in the real exchange rate. So now Taylor has shown that the half-life estimates that we get, they could be biased upwards as well, for two reasons. One is what is called temporal aggregation. Okay? So what does temporal aggregation mean? So if you use a model in which the real exchange rate follows an AR1 at a higher frequency than that at which the data is sampled. Okay, so what does this mean? So suppose we are using annual data. The data is sampled annually. But the real exchange rate follows an AR1 at the quarterly frequency. Okay? So at a higher frequency than which the data is sampled. This can create an upward bias in the estimated half-life. Okay? So the true frequency and the sampled frequency, they are different from each other. Too technical, we are not going to go into this. And then there can also be a substantial upward bias if we are assuming a linear adjustment when in fact the true adjustment process is non-linear. Okay? So these are two things to be aware of, but it's not really possible to do too much about this. So I'm not going to go into more detail. Instead, we will ignore. So I'm going to skip this section, the next few sections. So nonlinear real estate. So I'm going to skip this. You can just skip this. So if you are interested in this, you can read this, but I'm not going to cover this. The next section also I'm going to skip, 3.4. This is interesting, but if we have time, I may come back to this at a later stage. Okay, so I'm now going to go to modeling long-run deviation. So that is so when we try to solve the PPP puzzle, the PPP puzzle is why deviations, even if PPP holds over 200 periods, the deviations seem to be very persistent. Okay? So what is the cause of these persistent deviations? Okay? Over 200 years, right? That time horizon is too long. We are all dead in the long run, right? Keynes very famously said, in the long run, we are all dead. So what we care about is the short run and the medium run, not the super long run. So how do we explain these medium-term deviations, which are very persistent? And that's where the most important class of models which try to rationalize these long-run deviations from PPP is the Harrod, Balassa, Samuelson model. Okay? And this model basically says that, well, we should view traded goods and non-traded goods as distinct goods, separate goods, and try to model them differently because we only expect the law of one price to hold among traded goods. Okay? So the Balassa-Samuelson, Harrod, Balassa-Samuelson literature, it emphasizes the distinction between traded and non-traded goods. And it says, well, the existence of non-traded goods is the main reason why PPP systematically fails to hold. Okay? So the existence of non-traded goods so even in the long run, you would not expect PPP to hold for goods that do not trade. But when we study PPP, we look at the overall price level. That includes both traded and non-traded goods. And if PPP fails systematically for non-traded goods, then you may not expect it to hold, even in the long run. And if you need 200 years of data to find evidence that PPP holds, for all practical purposes, it really does not hold. Okay? So that's the idea. So we're going to see how the existence of non-traded goods can cause PPP to fail, okay, systematically. So I'm going to talk about this paper, Real Exchange Rates and Non-Tradables, which we distributed last time. So if the real exchange rate is stationary, then it should revert to its mean value, at least in the long run. But many researchers have found evidence against the hypothesis that PPP holds when general price indexes like CPI, etc. are used. Okay? And one important reason why the real exchange rate changes are so persistent is the existence of non-traded goods. So if PPP holds for traded goods, but not for non-traded goods in the long run, and if the weights on non-traded and traded goods are stable, then it turns out that the relative prices between non-traded to traded goods will move together with real exchange rates based on general price indexes. Okay, so I'm going to explain in more detail what this means. So let's move on to the econometric model. So suppose that we have a world economy with two countries. Country H is the home country. Country F is the foreign country. In each country there are two goods. Good N is non-tradable, so it's like a service, haircut, education, healthcare, all these are non-traded goods. Good T is tradable, so it's a commodity, could be computer, clothes, shoes, all these are traded goods. Then, suppose the general price index, so for each country, the home country and the foreign country, that's a geometric average of the price of non-traded good and the traded good. So, I'm going to write these equations in a simple way. I will not write the time subscript, okay, just to simplify